All right. Question number 1. Oh, by the way, this happens for the last 20 some odd years. Now, you can't go that far. Let's call it 18 to 19 years. I always start off with, okay, question number 1. And then I look at the question and I say, oh yeah. So how many of you felt that the reading was somewhat difficult for this material?
I'm not gonna lie.
No, please don't.
I'm raising my hand.
Okay. Well, I did a number of years ago, I'm talking like 15, 16 years ago, I did a reading level analysis of, oh gosh, it was 18 years ago, a reading level analysis of this assignment, okay, of the information in the book, okay. And I don't know if you guys know what reading level analysis means, but it essentially assigns a reading level of the material that you guys had to dig through, okay. There's a number of different ways to do that. Many of the methods, though, come up with some sort of formula that measures the number of syllables on average per word in like a sentence or paragraph. Okay? This assignment turned out to be a reading level 17.
What's
Out of however many years of school you're in.
Oh, wow. So I could do
I'll let you do the math.
So a lot higher.
Are we including here?
So that's 1 year out of college.
First year grad school is what the reading level of the section 4.1 is. No. Nobody counts. Anyway, moving on. So it's a pretty high level reading. Now remember I said though that a lot of them are based on number of, or average number of syllables per sentence or some such thing like that, right? First 2 words in question number 1. How many times did those come up throughout the whole thing? A lot. Electromagnetic spectrum. There's a lot of syllables in a very small space there. Would you agree? And that showed up like once or twice a paragraph, if I remember correctly. You know what I'm saying? So that reading level is kind of skewed a little bit. I'm still saying though that the information itself was somewhat difficult. So here we go. What is electromagnetic radiation? Anyone? Go ahead. This isn't the question. What is electromagnetic radiation? What are some examples? I think we've done this already this year. Well, the moon was reflecting a lot of it last night.
The sun.
The moon was not reflecting the sun.
Wait. How about some rays?
Visible light. Visible light. There's one. Ding, 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 ding.
X-rays.
X-rays.
Yeah.
Gamma rays. UV.
Oh, microwaves.
Micro.
Ultraviolet.
We got UV.
Oh, that's the same thing? Okay, you can't say all of you knew that. Come on.
Yeah.
Whatever. I'm sure there are
IR.
other people out there.
Infrared. Okay. But anyway, you guys, we've done this before, I think. Maybe not. Anyway, that's all electromagnetic radiation. Anyway, electromagnetic radiation has some properties of particles when it. I might put C.
Oh.
1. I may put B.
E.
And how many put D? Which if you put anything else, that means you have a chance of getting them all right. A is the correct answer.
I had it.
Who has
Madison did have
A? Who
it.
has A?
I had it.
Oh.
So we have 2 people that have the chance of getting. Nicely done.
One person.
Now, here's the thing. You guys got this piece of paper. You've done this before in a billion other classes where they give you this little worksheet on a section and the questions all go right in the order as you read through the packet, right? This was not one of those assignments. You ended up having to skip around quite a bit. You guys all saw something on that first page related to electromagnetic radiation and some other things, but the actual answer wasn't until like 2 or 3 pages later. Anyway, but there's that. And then let's talk about this. What is space made of? Essentially nothing.
Except
Now, electromagnetic radiation is, what is that? What medium? What is it? Electromagnetic radiation is a wave. Is a wave. What do waves need in order to transfer their energy? Through what does a wave transfer energy? Through a medium. But space has nothing.
it's still a medium though.
There is no, it's
No,
not a
it's
medium.
not?
A medium is matter of some sort.
They have
Okay?
waves
Currently,
in
we're
space.
able to communicate because what medium are we using? Air molecules, right? Sound gets transferred by air molecules bouncing off of each other, running into each other. You guys are familiar with this, I think. I hope. See, what I'm using this also for is to collect or fill all the holes that you guys came out of physical science with, and that's okay. It's all right. A lot of you know. Anyway, moving on. So, waves need a medium to travel through. There is no medium in space. There's nothing out there. So how, for example, does the sun's radiation get to us? If there's nothing out there to transmit that energy, right? Well, did you guys, as you dug in this book, did you guys notice that wave has two properties, or sorry about that, light? Did you see anything about the dual nature of light? Behaves as both a particle and as a wave. Did anybody happen to pick up on that? As you read through that? No. Some did, some didn't. Okay. Wave has a dual nature. Behaves both as a wave and a particle simultaneously. The only explanation for the light from the sun, for the radiation from the sun getting to us, is if light, electromagnetic radiation, has a particulate piece to it. And we're going to, you guys read about photons in there, right? That's what the photons are. They're the particles of light. Weird, huh? Light also has various other wave type properties. We'll get into that as time goes on. But anyway, that answers question number one. It travels through space because it behaves as a particle. Those particles are called photons, by the way, just in case you didn't pick up on that. All right, number two. Seriously, almost everybody misses number one. So if you miss number one, join 90% of the rest of the students for the last 24 years. Number two, the wave model of light was not able to explain. So basically we're having the same two questions here. Electromagnetic radiation has properties of particles because it can travel through space, and the wave model of light was not able to explain. Now, do waves have a frequency? You guys studied waves, right? Frequency, wavelength, amplitude, all those things, right? Okay. Can waves be interfered? Can they demonstrate interference? Right. So obviously A and C are out. I don't know if you guys know about the continuous spectrum. Did you guys notice the electromagnetic spectrum in your books? If you were digging into your books answering these questions, you had to see the electromagnetic spectrum in there. Okay? So C's out. So what are we left with? The photoelectric effect. Is anyone familiar with the photoelectric effect? Okay. As it turns out, many of you are. I'll demonstrate. How many of you have a garage door opener at home? Great. Well, an automatic garage door opener. I don't mean you as the garage door opener. Okay? An automatic one. How many of you have dead cats? From the garage door opener.
Oh, I thought
From the garage door opener.
Right, on that.
How many of you have a dead cat from the garage door opener?
why?
Good. Why don't you have a dead cat?
It has a
It has a sensor.
sensor.
Oh, I see
I
what
thought
you're
that
saying. Okay,
who just in
gotcha.
general has dead cat. Grandchildren cash, my favorite cat.
Anyway, do your garage door openers have a safety device on them? Yours doesn't. I mean, and then we run into that once in a while.
We don't have a garage.
Yours doesn't?
It does.
Oh, okay.
We don't have like a door opener. We like, what I do is I drive out and I go back in and I press it from the inside
And
and
then
I run and I
hop
hop
Oh yeah.
I like parkour.
Yeah. I got it.
Yeah.
I've done that. I've done that. Just don't hit your head. Well, you won't have to worry about it. That wasn't over your head? Moving on. So, has anyone ever helped anyone install a garage door opener before?
No.
Okay, there's a reason I was asking about that, because if you do, you'll understand how this all works, okay? But anyway, you guys, you know what I'm talking about? Those little, I think Gracie said some little sensors down there by the bottom of the garage doorway, right? Okay? So you guys knew that there's a motor that runs the actual garage door opener. And that's usually up in the ceiling above where your cars are parked, right? Okay? And then those little sensors of these little boxes over here. There's two of them. Now, here's always an interesting question. What's in those boxes?
A laser.
Pardon?
A laser.
No, not a laser, because if there were a laser, you'd see a beam, a very thin beam of light going across the garage door.
That would be cool.
That would be cool, but that's not there. Lasers are incredibly required, huge amount of energy. Huge amount of energy. Yes.
Are they infrared rays or rays?
Say this again?
Are they infrared rays?
No, they're not. No one's ever looked at your little boxes down there?
They're red. They look like
What's red?
the little light in them.
They are?
Yeah, both.
Both of them?
Oh wait, maybe one. I've seen a red one.
Okay.
I only see the one on the
Who
right.
has a red one?
I know there's a red one.
Anyone have a green? Okay, there's both. Okay, there's both green and red. Since I hate red, since it doesn't erase, I'm going to go with green this time. One of them has a light. Whether it's green or red, it doesn't matter. Okay, you can check this out when you go home. You just assume that if you see a light in one, there's probably a light in another. You never bother to look at it because we don't read our cereal boxes or our milk jugs. Just like, you know what I'm saying? You guys need to be pay attention to your world around you a little bit. Okay. On the other side, however, is a little piece of metal that looks like almost like a very, very small satellite dish. I don't know if you've ever looked at this piece or not. You gotta be a no. Okay, it's a metal of some sort. Now, we're gonna find out here really soon what kind of metal is it. Well, it depends on which color of light you have. Different metals go with different colors of light. We'll get to that here in a second. Okay? But anyway, so the light shines across, not a laser, but a light shine. So it's just like a little mirror almost, okay? So they have to be lined up perfectly. Has anybody's ever messed up their garage door opener sensors before? You know, you accidentally bump it, it doesn't work now or whatever. So, you know, these things happen. I do it all the time too. Anyway, so if something interferes with this sensor not being able to see that light, what happens? Well, this box yells up there, "Hey, go up!" You guys ever hear that? Well, then how does interrupting this cause that to tell the garage door to go the other way? And this is where, has anyone ever installed one of these before it comes into play? How does the information get from here to there? See, by now you guys should, with your world and the way it is now, what you guys have grown up with, oh, wireless. Well, that would be a good idea, but that's not actually true. It's not wireless. It's wired, okay? And so hidden behind some beams, and this is why I said, if you put one of these in, you would know, there's some wires that go all the way up here, okay? So that we have what we call an electric circuit. But the problem with an electric, well, what must be true with an electric circuit?
Oh, it's all gotta connect, and when something goes
We have to
it's
have a
like
continuous
disconnect.
path for the electrons to go.
Are there electrons?
We currently, thank you for noticing, we currently do not appear to have a continuous path for the electrons. We seem to have a big gap here. Now, Gracie said, oh, does that mean there's electrons going across there? In which case that would be a gamma ray, which is radiation from, you know, like nuclear decay, which we don't want gamma radiation. We don't want a laser, and we don't want gamma radiation going across there, okay? All it is visible light. Green in this case. Photoelectric effect. Turns out some obscure scientist who actually won a Nobel Prize. There's this one scientist that very few people know about that won one Nobel Prize.
Good for him.
And it was for the photoelectric effect. Let's see, what else did he do? You guys might be more over. Theory of relativity, E equals mc squared.
Einstein.
Einstein won one Nobel Prize for something you guys didn't even know about until about 48 hours ago. Photoelectric effect. He's the one that figured this stuff out. What basically this says that if light has a specific frequency, when it hits a metal, it can cause electrons to be ejected from that metal. And now if you provide a path for those electrons to go, they can work their way around. And there we go. So that's what completes the circuit. The electrons are being generated from that little piece of metal there. Interesting, huh? Okay, photoelectric effect. So once again, it goes down to light. Photons are able to eject, particles are able to eject other particles, electrons. We're going to spend next few days working with stuff like that. Where did I put my paper? Found it. Next, sub. Number 2 is D. Anybody 1 for 2? Anybody 2 for 2? Still the same 2. Still the same 2. Yeah.
Okay, so like when you click it on, what happens to make it go up? When you click it off, what happens to it?
What are you talking about?
Like the
Clicking.
clicking the little thing.
Oh, well then that's a whole nother electrical system. So when you press the button on your,
Yeah.
or you're talking in your car, now that's radio.
I don't understand how electricity works, so I don't know.
Okay.
It's black magic. Like,
I understand
how
that.
does it go through the cords? How does
Wait,
it
why is it not on top?
Take AP chemistry. Oh wait. Okay, moving on. For number, or take physics. Take both.
At the same time.
Number 3, in wave motion. Now this you should all get right. This is straight from your physical science class. In wave motion, the product of frequency and wavelength is equal to. I hear a B. Anybody for a B? Speed of the wave? And that is precisely correct. That is precisely correct. Now, there's a couple of equations that we're going to look at today. This is one of them. Now, way back in your beginnings of your physical science, you guys learned about speed. Does anyone remember the equation for speed?
Distance over time.
Speed equals distance divided by time. Okay, and if we were looking at a unit, we were looking at meters per second as a fairly typical thing. You guys did a lot of calculations like that, right? Great. This equation, though, says for to calculate the speed, it's the product of frequency and wavelength. Product, the word product is associated with what operation? Multiplication. This would be a division, quotient, right? So what's this equation then? Well, it said speed, I'm going to use C. Remember we've talked about C for speed earlier this year? E equals mc, speed of electromagnetic radiation in a vacuum, okay? Says it's equal to the product of wavelength and frequency. So in other words, C equals lambda nu. This is important. Add this to your notes. C equals lambda nu. Now we've already discussed that C is the speed of electromagnetic radiation. Does anyone remember the value for that I gave you earlier this year? You may not have written it down. You probably ran across it in the book as you were reading through this. Does anyone remember that though? Okay, that's all right if you don't. I'm going to give it to you as 2.9979 times 10 to the 8th meters per second. I think your book says 3.00. That's fine. It doesn't really matter. But as as I've said to you guys before, I like my constants to have more significant figures than what my normal measurements are going to have. That way it doesn't limit significant figures. Anyway, this is all those things we talked about earlier. X-rays, microwaves, infrared radiation, UV light, ultraviolet light for that matter. They all have that speed in a vacuum, which basically means in space. Okay? This right here is the Greek letter. Does anyone know that one?
Looks like a
It's lambda.
Yeah, you just said it.
Yeah, I did. Greek letter lambda, it refers to wavelength. And wavelengths are measured in meters as a standard, okay? Measured in meters. Oh, wait a minute, that's good. Speed and distance are directly related, just like they are here. Would you guys agree? Speed and distance directly related, speed and distance directly related, okay? But now we've got this thing with this is the Greek letter nu, by the way. I don't know, this is new to you.
Boo.
Greek letter nu, and it refers to frequency. Okay? You guys get frequency, you really do, but you've never thought about frequency. Could anyone give me a definition or explanation of frequency?
It's kind of like how often something happens in a certain amount of time.
Per unit time. The number of occasions per unit time. What does the per usually mean, mathematically? Divide. Okay. So the unit for frequency is is 1 over 1 second. So we can have, how often do you do your homework? Well, for Alicia, that would be 0 per unit time. If that were Christina, it would be many per unit time. Just kidding, Alicia, just kidding. Okay. But there's another way that this is, so there's our time in our denominators. You guys see where that happened? So even though we're multiplying, we can get away with multiplying because the time's in the denominator like it should be. Okay? Now, there's a lot of times you're going to see it written this way. I don't know how familiar you guys are with looking at units written that way. It means exactly the same thing. And like so many times, they ended up naming this unit after an old dead guy. Some of you are familiar with this person. It is not Newton. He's with something else. Oh, I thought maybe you would know. Madison. What radio station do you listen to in the morning?
I don't.
Oh. Leah, what do you listen to in the morning?
97.9.
97.9 what?
WNC.
No. 97.9 what? So number's got to have a unit with it.
AM or FM? Oh.
I know. This is why I'm asking the question, Alicia. Megahertz.
What?
Megahertz. 97.9
MHz.
megahertz, which means
Right.
1 million hertz.
Because it says MHZ.
It does. It does.
If you
That's
have
it.
the, if you
See?
have the right radio.
Have you ever looked at your cereal box before? No, I'm just saying because you paid attention. You saw a
Yeah.
number, you saw a bunch of letters after it, but you actually remembered that. That's good. All right, so anyway. So now, interestingly, look at all the Greek letters we now know. We learned earlier this year, we learned this one, which is
You.
mu.
And then alpha, gamma, delta.
We've learned delta, right? We've just learned lambda and nu. You guys probably already know sigma. You guys know
Yeah.
sigma?
And alpha, gamma, delta is my mom's sorority.
What's that again?
Get the little babies.
Wait. Gracie, what's that?
What?
Say what you said.
I don't want to. You're gonna make fun
No,
of me.
no, I'm not actually. Say it.
I said, wait, alpha, gamma, delta is my mom's sorority.
Oh, really?
Yeah.
That's weird.
Why do you know that?
Because that's my ex-wife's
Is
sorority.
her name Liz?
It is not.
Very.
It is not. It doesn't matter. Moving on. Let me see. Oh, and then later we're going to learn the lowercase for sigma, which looks like that. We're going to learn the lowercase for delta, which looks like this.
Small sign.
Ah.
Don't confuse me.
Yeah, that's about it. Okay, so anyway, moving on.
My question is, there's so many Greek letters. Why do they use the same ones and change
Yes.
them from different
Because there's so
subjects?
many things. There's so many things.
Okay.
I mean, there's just so many things. Anyway, moving on. This is a highly, highly important equation for you. If you have not written that down, please write that down. The one that I have a big purple box around.
Yes.
All right, next. We're currently through question number 3.
Wait.
Chapter 4.
It's
No.
really, it's, yeah, I looked at it and I was like.
Number 4.
what?
The common characteristics shown by X-rays of light, infrared radiation, radio waves, UV light, ultraviolet radiation, I'm going to keep saying that one over and over, is that they all have the same speed. C. Is anyone still 4 for 4? You can't be 4 for 4.
That's Wendy's.
You missed the first question.
No, she had A. I had A.
Then why did it? Okay, you never raised your hand.
For A? I said I had A.
Okay. Anyway, so 3 of you still 4 for 4. Awesome.
Who's the other?
Anybody 3 for 4?
Jabez.
Or better. Or better. So that's most of you. Great. Number 5. Red light has a longer wavelength than blue light. Compared to the blue line on the hydrogen spectrum, the red line would represent, what'd you guys all come up with?
I had D.
Everyone shout it out.
D.
D?
D. Number 5?
Oh, really? Wow. That is correct. How'd you guys get, just out of curiosity, I've had a lot of people struggle with that over the years. How did you guys come up with that?
Maybe site. That is true. I was looking at them.
Okay, Zach, are you any of you psych?
Yeah.
Okay. Did you put D for number 5?
Yeah.
Okay, why?
Skim and scan and then guess.
Okay, no, but seriously, so you did a little, all right, anyone else want to offer an explanation? I'm curious, I'm curious, because again, rarely do people come up with that. Go ahead.
I was looking at the picture in the book.
Okay, and they did have a nice picture in there. They did have a nice picture in there. So you just thought about it. Awesome, thank you for sharing. So you mean if you do spend some time looking at that stuff, it makes sense. All right. Great. I want to talk about that though, because there's a relationship that I want to. It's time to do it. I need volunteers. So Jake, you look good. Whoa. Unless Madison wants to do it. You want to do it? Turns out my one piece of tape is incorrectly placed, but that's okay. Now, Jake, I'm happy about one thing. A lot of times when people get this, they see that little ring and they put their finger in that. Don't do that. You will lose the finger. Okay? Hang on tightly. I cannot emphasize enough. Hang on tightly. I'm going to go all the way back with your rear end up against that
Okay, I
counter.
don't like that there's hot water.
Okay. Hang on
Let go.
tightly.
Don't let go.
Okay, now, I am going to make Jake's hands move. It's magic. Watch this. Move. Oh, well, that didn't work. Let me try again. Move. Still didn't work. Oh, there they move. Now, why did your hands move? I did that. So some energy got transferred from me to you through a medium. What was the medium? The spring, right? You guys with me on that? Okay, so now that's what waves do. They transfer energy from one place to another through some sort of medium. What are the two main types of waves you can have? Okay, again, I'm using this to fill in some holes.
I know it's not visible.
Oh, longitudinal. Actually, I'm going to let go.
Oh, that's what you meant.
Longitudinal.
Okay.
Now, again, I'm filling in holes here.
I didn't know if you
No,
meant.
not that. So longitudinal. Now, let me show you something here. Now, remember longitudinal waves, you may have seen drawings that looked kind of like this. To represent longitudinal waves. Does anyone recall that? Okay? And what happens there is that, let's say the direction of the energy travel is horizontal. In a longitudinal waves, which direction are the particles traveling? Look what's happening here. And maybe either you and or your teachers did a demonstration or an experiment where you took like a slinky possibly, and maybe either moved the rings and or moved your hand back and forth, and energy got transferred from one place to another. Which direction were those particles moving?
Left to right.
Left to right. So also moving horizontally. Would you agree? So in a longitudinal wave, the particles and the energy are both moving parallel to each other. Look at the word longitudinal. What letter is this?
L.
What letter is this?
No.
How are they oriented relative to each other? Parallel. So longitudinal waves, the particles travel parallel to the direction of the energy. What was the other type of wave?
I know it goes like
Okay,
that.
it goes like this. Okay, so let me do a little thing here. Something like this.
It's
Okay.
not like the troughs and the.
Oh yeah. Okay. What type of wave was that called? Okay, now watch this. Let's again say that the energy is traveling from one end to the other. Would you guys agree? But each particle, now what does this represent right here? Does anyone remember? That's the rest point when Jake and I were holding the slinky, it was pretty much straight across. That would be the rest point where nothing was going on. Okay? Where did the particles, how are they traveling? Well, it turns out they're traveling, if you were to have able to focus on one of those particles, like say a piece of tape, you would find that the pieces of tape would be going up and down, whereas the energy is going horizontally, or in what orientation relative to each other? Perpendicular.
Is that what it's called? Oh, Oh.
And the T, the parts of the T are perpendicular to each other.
Is it transverse or transversal?
Transverse.
Okay.
Okay? So transverse wave, the particles move perpendicular. You can use the T to help you remember that. In a longitudinal wave, you can use the L's to help you remember that the particles move parallel to the direction of the energy travel. So anyway, obviously where am I going with this? What were Jake and I going to go back and demonstrate again? What type of waves do you think? Transverse or longitudinal? Transverse. Jake, come on back. You're not even close to me, John. This one goes. Okay, so if you can watch the little pieces of tape which represent the particles, tell me which direction they're going to be moving. I think the one in front of Leah, oh, by the way, just out of curiosity, how many waves are currently being demonstrated in that transverse wave that's on? It is not two.
One.
It is not three.
one and a
It is
half.
not one. 1.5. Because remember, a wave has to go through a complete cycle, up, down, and back, and then it goes one more half. Does that make sense? Okay. So to have a complete wave, you have to have the same number of troughs and crests. Okay, here we go. I'm going to make a transverse wave. Give me a second. It takes a little while. Hang on. Okay, so here we go. We have a nice standing transverse wave. Which direction are the pieces of tape moving? Leah, you definitely have a good, you can tell, straight up and down, right? For the most part?
Yeah.
Okay. And you guys back there can probably tell the same thing. Can you, Caleb? Yeah? All right. Now, how many waves are currently being produced?
1.5.
Just one. Just one. There's one trough and one crest. Would you agree? Now, they keep switching places. I get that. But there's one of each at any one point in time. Okay? Jake, try not to move your hands. Seriously, okay? Now, give me a second here. But what I'm going to do is increase the frequency. I'm going to increase the frequency. Meaning what? I'm going to put more waves in there. What are you guys going to notice? It won't go faster. It can't go faster because it's the same medium. What's that, Caleb? The wavelength is going to decrease is what he meant to say. But that's exactly right. Okay, the wavelength is going to decrease. Give me a second here, people. It takes me a little while to get this done. Hang on. There's one other thing that should be very observable, but not by you guys. It's probably going to be the Jake that finds this out. Now, are there more waves? Jake, what do you notice? Is there anything else you notice? What are your hands doing? Why? Okay, but what I'm saying is, how much energy got transferred to you? A lot more? Excellent. Walk towards me.